Hi, we are Team Wesew and we will be talking about forging today. Forging is a manufacturing process involving the shaping of metal using localized compressive forces. The blows are delivered with a hammer, often a power hammer or a die. Forging is one of the oldest known metalworking processes. Traditionally, forging was performed by a smith using hammer and anvil. The smithy or forge has evolved over centuries to become a facility with engineered processes, production equipment, tooling, raw materials, and products to meet the demands of modern industry. Forged parts can range in weight from less than a kilogram to hundreds of metric tons. Since the Industrial Revolution, forged parts are widely used in mechanisms and machines wherever a component requires high strength. Forging is carried out in many different ways. One way to classify the operations is the degree to which the flow of the work metal is constrained by the dies. By this classification, there are three types of forging operations: open die forging, impression die forging, and flashless forging. In open die forging, the work is compressed between two flat or almost flat dies, thus allowing the metal to flow without constraint in a lateral direction relative to the die surfaces. In impression die forging, the die surfaces contain a shape or impression that is imparted to the work during compression, thus constraining metal flow to a significant degree. In this type of operation, a portion of the work metal flows beyond the die impression to form flash, as shown in the figure. Flash is excess metal that must be trimmed off later. In flashless forging, the work is completely constrained within the die and no excess flash is produced. Another way to classify forging is by working temperature. Most forging operations are performed hot or warm, owing to the significant deformation demanded by the process and the need to reduce strength and increase ductility of the work metal. Some other parameters to classify forging is based on processes that relate to forging, like swaging, roll, and orbital forging. Based on heating style, it could be divided into isothermal forging and induction forging.
Now we focus on the closed die forging, or sometimes called impression die forging. The process is illustrated in the three-step sequence. First, place the workpiece on the lower die. Then, drop or press the upper die downwards. As the die closes to its final position, flash is formed by metal that flows beyond the die and then into the gap between the die plates. A closer look of terminology for forging is shown in the right picture. The maximum force that applied to the upper die is determined by three factors: the projected area of the part including flash, the flow stress of the material YF, which in the hot forging equals to the yield strength of the material, and a forging shape factor KF, which can vary from 6 to 10 in terms of the complexity of the part's shape. For most parts, several forming steps are required in the closed die forging to transform the starting blank material into the desired geometry. Several cavities in the die are needed for each step. As you can see in the animation of an automatic bolt forging process, before the bolt is formed into the desired shape, three intermediate forging processes are applied on the bolt, and the dies for this process are called performers or blockers, while the last die is called the finisher.
Okay, so let's see what is real closing die forging looks like. Now you can see, for a particular part, a crankshaft, the raw material is preheated and placed on the workstation. Then the worker placed the material into the die mold. The upper die is on the hammer. The hammer will then punch the raw material and force it to transform into the crankshaft shape. Then the crankshaft will be transferred to another worker for further process, usually for coating and finishing process. Now let's take a look at what happens when the die is closed. The blue color here indicates the compressed force that the upper die on the hammer gives to the raw material. Two die closed and the material shaped into the crankshaft. Depending on the complexity of the parts, this process may be repeated for several times, just like what you'll see in the previous video. Since the closed die forging is not like the flashless die forging, it's not absolutely sealed. Extra material will squeeze out when two die close together, which will form what we mentioned before, the flash. Here you can see the gray color indicates the flash, and also there's still some flash inside the die mold. Actually, the flash will be removed later, usually by trimming process. Although it is a waste of material, the flash is still important. It cools more rapidly than the rest of the material in the die. This cool material will become stronger than the material in the die, which helps to prevent more flash to form. The flash can also force the metal material to completely fill the die cavity. In fact, the flash is also need to be carefully designed.
Now I'm going to briefly talk about the service temperatures that are encountered in forging. As can be seen from the table, we have the alloys enlisted with the corresponding temperature range in which they are forged. Clearly, as can be seen, the temperature range varies from 1600 Fahrenheit to 2400 degree Fahrenheit. As discussed before, forging can be distinguished into three types depending on the service temperatures. For hot forging, the temperature has to be above the recrystallization temperature, which is defined as the lowest level of heat at which the distorted grain structure of a metal is replaced by a strain-free grain structure. For warm forging, the temperature is below the material's recrystallization temperature but above 30% of the recrystallization temperature on the absolute scale. Whereas for cold forging, the temperature is below 30% of the recrystallization temperature, usually the room temperature. The graph shows the relative advantage hot forging has over the others. In hot forging, as the material is deformed, work hardening effects are negated by the recrystallization process. This results in much lesser stresses in hot forging than cold forging in particular.
Designing the forging die can be regarded as one of the most important jobs. As shown in the picture, this kind of shape is the most economical shape to forge, which can be formed in impression moving in opposite directions. However, if you want to design parts and dies like this unbalanced shape, the forging can generate a side thrust in the die. So in this case, a counterlock is needed to prevent the lateral sheet of the die. However, the counterlock is subject to wear from the side loads. So the solution to this is to design balanced dies. The left design is balanced in dies, but if there are holes in the bosses, then the holes must be machined in a secondary operation. The right design can solve the balancing problem and also allow the holes to be forged simultaneously. Once having the geometry of the desired forging part, the die designer first designs the finisher dies by selecting the appropriate die block size, the flash dimensions, and estimating the forging load and stresses using FEM to ascertain that the dies are not subject to excessive loading. Also, there are limitations of part design, including the corner and fillet radii, which usually due to the material and the shape of the workpiece. As you see in the upper picture, the nickel alloys requires more radii and thickness in corner and ribs than the aluminum alloy. And the table underneath shows the representative radii for forging parts with 1-inch high ribs. For example, the stainless steel preferred to be forged with at least 6 mm radius fillet, while the titanium is 13 mm. One of the most important processes in die design is designing the preform or blockers, which is an especially difficult task, requiring skills that can only be achieved by years of extensive experiences. The basic rules for preform design is: first, be aware that the area of cross-section of the preform equals to the sum of the cross-section area of the finished parts and the flash allowance. Second, the preform radii should be greater than the finisher radii in the same position. And third, the thickness of preform should be greater than the finished parts, so that the metal flow is mostly by upsetting rather than lateral extrusion. Also, for different heights of ribs, different numbers of preforms are used, and again, this may require time for experimental trial and errors.
Heat treating is often employed to develop properties in the forging that could not otherwise be realized with the selected alloy. Although it is most often associated with ferrous alloys, forging alloys in all of the 7 major alloy groups can be heat treated to advantage. Forgings are generally heat treated in the same process that are used for castings and weldments. The need for heat treating is sometimes eliminated by using an alloy that develops the required properties in the as forged condition. For example, microalloyed steels are sometimes used to reduce or eliminate heat treating operations that would be required for carbon steels. However, the purchase price of forging stock is higher and some additional costs may be incurred due to requirements for additional air cooling equipment. The optimum combination of alloy and heat treatment is best developed in discussions between the forger and the purchaser. Generally, an alphanumeric sequence is used as a system for designating heat treatment for forgings. One such example is on the screen. Depending on the service temperature and percentage of carbon in the forged material, heat treatment could lead to processes like normalizing, process annealing, spheroidizing annealing, and hardening, as is clearly seen in the graph, also famously known as the iron carbon diagram. The common materials that are used in forging which are heat treated are stainless steel, titanium, and aluminum. For steel, annealing and austenitizing processes are generally employed. While the former reduces hardness, the latter increases it. Heat treatment on aluminum is also mainly done to relieve stresses and improve the mechanical properties. For the titanium alloy, which is forged at temperatures between 595 and 705 degrees Celsius, heat treatment is necessary to remove the built-up residual stresses. Between them, upon heat treatment, titanium alloy has the highest strength to density ratio as compared to steel and aluminum, which is the least in the group.
To talk about the forging cost, there are 5 basic aspects. Material cost, which is always the most important. The operating cost of the equipment are depending on the equipment selected for the forging, and requirements must based on the load or energy required for the shaping the parts. Say you want to have a 3 tons forging machine or 13,000 tons forging machine, all depend on design. Other costs like manufacturing costs involves the labor cost or head cost. The second cost involves multiple costs for finishing operations for the forging part. Since the tolerance of the forging is sometimes very low, many extra processes are needed. Also for the quantity cost, the cost involves the design for the forging process or the software cost. The material cost of the forging will depend on the design of the forging parts. Usually, half of the cost is the material cost, and 30% of the material cost is the wastage cost, cost of the flash, punch outs, and other discards during the manufacture process, which is also important consideration when you do the manufacture material cost estimation. Among the same class of the manufacture process, forging process has many advantages as well as trade-offs. For our part, the crankshaft can be also made by using investment casting. Those two can use similar materials to produce similar parts. Compare between those two, forging requires more operating steps as well as the finishing step because of the low intolerance, while the casting could result in higher tolerance for the requirements. Another aspect of those two processes is that although they can use similar material and produce similar parts, the result in the quality of the part is different. So here you can listen to the difference between the same products. During the forging process, the part is made when the raw material is still in solid state. It refines the grain structure and develops the optimal grain flow, which imparts the desirable directional property such as strength and fatigue. Also, porosity in casting process can be eliminated in the forging process, which makes the part more stronger.
Finally, to conclude, we see that forging is one of the most important manufacturing operations. Research is focused on reducing the tooling complexity, costs, and making it environmentally feasible. Thanks for watching our video. This is Team Wesew signing off.